Hi, my name is Steve Piccolo. I'm at Brigham Young University, and I want to talk to you about my experiences learning about CWL, authoring some CWL tools and workflows, and my general experience with that. I'm going to talk about opportunities for using CWL in a way that maybe it hasn't been used as much, and I'll talk about what I mean by that. And I'm also going to briefly talk about a web-based CWL authoring tool that I've created. In my research, I work on cancer genomics and related questions. Two of my collaborators shown here are Andrea Bild, who's at the City of Hope Comprehensive Cancer Center in Southern California, and Jeff Chang, who's at UT Houston. Their research focuses on using cancer genomics or DNA sequencing to understand how tumors evolve and how we can more effectively treat those tumors by looking at the mutations that are evolving within a tumor. So as new patients are treated or new samples come in for these patients, they want to be able to sequence the DNA of those patients really quickly and then start being able to adapt therapies for those treatments as quickly as possible. So I've been working with them on a pilot project through their grant, and have worked on CWL as a solution potentially to help them speed up this process, scale it out to the cloud or other potential resources like that. Traditionally, what I've done with these types of tasks is written a bash script, something like this, to be able to take FASTQ files, so the raw data files, send them through various different tools in order to identify DNA variants that are present in those tumor samples. And that's worked fairly well. And a few years ago, Docker came onto the scene, and that has a lot of promise and gave us an incentive to try to use it because it gave us an opportunity to use the same pipelines or generalize the pipelines so that they can be used on multiple different servers that may be in different geographical locations and have different configurations. So we started looking into this, and I even wrote my own pipeline tool, which I guess every bioinformatician has to do that at some point. And then I went to a workshop at the ISMB conference in 2019 and learned about CWL and have been digging into it ever since and see it as a great resource, a great way to standardize pipelines. Okay, so I dug into the documentation. I've been learning about it and kind of coming to this from the perspective of a practicing scientist, somebody who wants to be able to process large data sets, but I was also thinking about generally how CWL is used by the community or how it might be used. And so as I thought about this, I considered two main types of tasks that people might want to perform and use CWL for in support of computational reproducibility. So one type of task, which I think is the main focus of people who use CWL at this point, at least that's my perception, is to perform batch processing of large data sets. So this is like I was talking about being able to process these DNA samples quickly and have what I would call a canonical tool or workflow that I can say, here's exactly how we want to process it. We've described it in this document. We can run all of our samples through that same pipeline. Okay, and so this type of task typically requires lots of computing resources, maybe scaling it out to the cloud or a cluster computer, and it's going to use mature-ish software, so software that's not going to change that often. Okay, but again, we're going to try to process this on apply this to many different data sets. Another application of CWL, and my perception is that CWL is not used very often for this type of task yet, is for reproducibility of research analyses. So if you're analyzing a data set, say to identify genes that are interesting to a particular phenotype or something like that, you're going to need to import the data, perform some statistical calculations, use some existing packages in the R programming language or Python or something like that, create some visualizations of the data, and then you will include that potentially in a publication. And a big push these days is to take that analysis and make it available to other people and make it so that they can easily reproduce what you did. So if you're performing this task this is a custom task, something that will be applied only to, or at least this particular analysis will only be performed once to that particular data set. It's generally going to be an analysis, or often will be an analysis, that can be performed on a personal workstation rather than needing to be performed on cloud computing or a cluster computer. This diagram shows the main components that would go into that kind of an analysis. Generally, you're going to have a script. So in this case, I'm showing a script that was written for the R statistical package. It's going to use the base R packages as well as some additional packages you might want to use to perform your analysis. You're going to want to execute that script at the command line, and that script is going to go and read data probably from some input files either on your file system or out on the internet. And then in the end, you hope that it will produce some output files that are the basis for your analysis. And those could be text files or they could be graphics files. So let's say that I was going to perform what's called a gene differential expression analysis. So the idea here is that I want to identify genes that are expressed differently between two conditions. So let's say in this example, we're looking at 2 strains of mouse, and we want to see which genes are expressed differently between those strains of mice, and that can tell us something about the underlying biology or how those mice behave differently from each other. So to do this analysis, I would write an R script, and I'm just showing a portion of this script here. I'm going to import some libraries. I'm going to accept some arguments into the script. I'm going to read the data in and perform my analysis. I'm going to need to have a certain formula that I would use that would represent the analysis that I want to do. Okay, here's an example of a data file that I might use. Each row in this file would represent a given gene, and each column would represent a given mouse. I would have a separate file that would indicate phenotypic data. So which strain each mouse is, and this is only showing a subset of the data. They're all the same strain in this example. And additional experimental information that I can use in my analysis to try to remove technical biases that might influence my results. I would use maybe this package here, DESeq2. There are other packages that are available, but let's just say I use this package to perform the actual statistical calculations. And then I would use the tidyverse packages, and these are packages in the R statistical package that I can use to manipulate data and create some nice looking graphics. Okay, to work with all of this, or to package this all up, or my execution environment, I should say, for this would be a Linux operating system that's encapsulated within a Docker container. So I would write a Docker file, something like this, and this is just a really simple one because I'm inheriting from an existing Docker image that the Bioconductor Consortium has created to make it easier for me to do this. So all I have to do is run a couple of commands here to install the DESeq2 package and then the tidyverse packages. Once I've generated that Docker image, or within that Docker container, I can execute a script kind of like this. We're going to pass in some arguments, tell them which files I want to use, and what formula I want to use, what my output files are going to be, and so on. And in the end, I'll get a table that looks something like this. I'll have a bunch of genes listed. I'll have some statistics for each gene, including a p-value for each gene. And then I can write up my paper based on these results, maybe make some graphics that look like this. This is called the volcano plot. So I have all of these pieces that I need to bring together in order to perform this analysis. When I do it, I can do that all on my computer, but if I want to be able to share my analysis or make it reproducible for other people, I need a convenient way to package all of those different components together and share that with other people so that they can observe exactly what I did and even reproduce my analysis and get exactly the same results. I see CWL as an opportunity to do that, to package everything together into a single document that I can then use or share with other people. I may not put my actual data files in there, that depends, but at least all of the computing logic that I need for my analysis. As I work to tackle this, to do some proofs of concept for doing this, it felt a little bit like an uphill battle. Not that I'm trying to say anything negative about CWL, it's just that it does take a little bit of time to really wrap your mind around how do you use CWL, how do you adapt it to, for example, to an analysis like I just described. Okay, and there's some really good tools out there, tools for workflow engines for executing tools and workflows. There are tools out there for authoring CWL documents. And mostly what I see in those tools are tools that are designed for people who want to use code to generate these. So there are libraries in various programming languages that you can use to generate CWL documents. There are plugins that you can use for code editors, but again, that revolves around coding. And then there's the Rabix Composer tool, which is very powerful, but in my view is sort of more suitable for somebody who's really familiar with the details of how CWL documents are structured and just all the terminology that you would use in a CWL document. So what I set out to do is create a tool. It's a web-based tool. It just runs within your browser. There's no server-side component to it. It's just HTML, JavaScript, and CSS. And the idea here is to create a tool that will enable researchers to generate what I guess I would call a simplified CWL document. There's still CWL documents that conform fully or conform to the CWL specifications, but they're sort of a specific flavor of CWL documents. And the idea here is to use a subset of those components in CWL in order to enable researchers to make CWL files in a way that I hope will be intuitive to them. I'm going to take you on a quick tour of this app. So it's called ToolJig. And at first you'll see an explanation of what this tool is designed to accomplish. If we scroll down, we can upload an existing file if we want. And then the next section will enable you to input basics or metadata about the tool. This particular example that I'm showing you is for a tool definition or tool description. There is a separate app that I've created that will enable you to create workflows. I'm not going to demonstrate that today, but it is there. Okay, so we can input things like label, documentation, a Docker file, which is required, author's information, as well as a license for this document that we're creating. In the next section, we can manage inputs. So if I click on this, it'll show you that I can specify a name, a type, or documentation for each of those inputs. I can add and remove them. Auxiliary files, these are like, in this case, it would be my DESeq2 R script. I can go and input this here, and then it will be incorporated directly into my CWL tool description. In the next section, I have something that I call a command template. And this is an example where my flavor, or our flavor of CWL differs from what many people use in that we don't use the base command option within CWL tool descriptions. I use the arguments section only. And this gives me flexibility to make it so that users can specify the command or commands that they want to be executed within the container, and they can use the inputs as placeholders for this command. It just, to me, as I was using this, it made sense to do things this way. In the tool itself, we also provide some validation. We use validation to verify that they've specified each of the inputs and give them a little bit of help in knowing how to specify those. In the next section, we manage outputs. I'm just going to skip through that. And then at the end, you end up with, if you've inputted everything that you need to, you'll have a CWL document that you can then download and run on your computer or on a remote computer. Lastly, we also enable you to create an input object file or a job file, and it's dynamically generated based on the inputs that you have in your tool. You can download that file as well. Thank you for listening. I'd love to hear any feedback you may have on the tool, on how to make it better or more useful for the community, maybe additional features that you think would really help it to be adopted by people within the community. I'd love to also hear your feedback on using CWL as a tool for reproducible research analyses. Thank you for listening. I hope you have a wonderful day. It's great to be part of the CWL community.